So last time we talked about partial derivatives and how do we calculate partial derivatives. And today what we're going to do is we want to continue to talk about the meaning of differentiability of function of two variables, which turns out to be a bit different from a function of single variable. So let's look at one motivation example here. Find out the area when we calculate the area of a rectangle. With length x and with width y. So when you calculate the area of a rectangle, the length may carry some error and the width may carry some error as well. Let's find out the area of the area. If the arrows are delta x and delta y. So there is this arrow delta x and arrow delta y. Well, the accurate area is this function of two variables, just x times by y. The arrow denoted by delta f is when there are errors in the length and the width. So we're going to use this to subtract the actual area. And will you FOIL this out and subtract terms? You have this arrow part which appears to be linear, okay? It's a linear function of delta x and delta y. And then you have this delta x times by delta y. So this is the actual error. And this piece here is called relative error back here. This one right here, which appears to be a high order term, delta x times by delta y. This is what we call a relative error. So this high order term appears that we can ignore this one. So the delta f can be approximated by the linear part. All right. So this is the actual error, but this is the we can probably approximate it with this term. And here's what we noticed. If we approximate delta f with this linear term, it has the following properties. It has the following properties. Number one, as we said already, it is a linear function of delta x and delta y. It is linear. Number two, the relative error, okay, the relative error goes to zero, okay, goes to zero faster than both delta x and delta y because of the product. And which turns out to be the key to define differentiability. Relative error goes to zero faster than Faster than I guess the linear part. Now, if delta x goes to 0, this part goes to 0, well, it'll just be faster than delta x. It's also faster than delta y. So we'll simply say relative error goes to 0 faster than this. And notice this is really the linear term of delta x, and this is also linear term, linear part of delta y. Goes to 0 faster than this. What this actually means is if you take this piece, divide by this guy, and let delta x, delta y goes to 0, this ratio, okay, will goes to 0. All right, so think about this part, okay? Think about this part. And this turns out to be the crucial part to define differentiability. If there's a linear function, all right, we call this linear function L, a linear function of delta x and delta y, which turns out to be given by the following formula, okay? Given by the following formula. Partial derivative of f with respect to x evaluated x naught, y naught. So that's a number, okay? That's a constant. It's a constant times by delta x, and another constant times by delta y. So that's a linear function of delta x and delta y, which is given by this formula here. Once again, this is a constant here, so this is another constant times by delta x, delta y. Such that when you subtract f with the function's value at x naught, y naught, so that's like the arrow part. So that's like the arrow part using the previous example. And this arrow can be approximated by this linear part, okay, this linear error. So I just use L, delta x, delta y. Plus, well, some higher order terms, okay, some higher order terms. So what we're going to do here is I will use higher order terms to denote the higher order terms by epsilon 1 delta x plus epsilon 2 delta y. So the key here is we don't really know what epsilon 1 is, epsilon 2 is. They are not constant, okay? Those two guys, they're not constant. They are just some expression, okay? They are some expression. So the key here is I'd like to isolate out the delta x, delta y. So the key here is I need this guy goes to 0 faster, okay? I need this guy goes to 0 faster than the linear part. So in which those two coefficients, epsilon 1, epsilon 2, they're no longer going to be constant like 1 or 2, okay? Instead, they have to become very small. They both goes to 0 as the linear error delta x, delta y goes to 0. So when delta x, delta y goes to 0, the actual error can be approximated by linear error, okay? Linear error. Plus some higher order terms, that goes to 0 a lot faster than the rate that delta x, delta y goes to 0. All right. So the key here is epsilon 1, epsilon 2 has to go to 0 as delta x, delta y goes to 0. And based on this definition alone, okay, based on this definition alone, if a function is differentiable, then the partial derivatives automatically exist because that's part of the definition here. But not the other way around, obviously. Okay, so quick remark. based on the way that we define differentiability, if a function is differentiable, then the partial derivatives exists at that point. In other words, if the partial derivative does not even exist, this guy cannot be what? Cannot be differentiable. Okay, cannot be differentiable. So I like you guys to show. I like to show you guys two examples explaining the meaning of differentiability. So here's the function of two variables. Is this one even differentiable at 0, 0? So that seems like a very tricky thing to do. But what I want to do here is I will show you the actually the partial derivative does not even exist. The partial derivative does not even exist. So I will go ahead, I will try to calculate the partial derivative at 0, 0 with respect to x. Let's think about what that means. Partial derivative with respect to x, right? So we're going to subtract the function's value at 0, 0. We're going to keep the y value the same. We're going to keep the y value the constant, give x some change. So this one becomes f of h 0. The y value is kept the same. Divide by h and let h goes to 0. And that's how the partial derivative with respect to x is defined. All right, that's how the partial derivative with respect to x is defined. Because y here is set to be 0, so the y here is always 0, so this actually just becomes square root of x squared. And the first part we plug in h, you actually get h sub's value. This part is 0. So you're talking about the limit of this. As we all know, this limit doesn't exist. Okay, as we all know, this limit does not exist because there are two-sided limits here. When h goes to 0 from the right side, it approaches 1. When h goes to from the left side, this goes to negative 1. So I will simply just say this limit does not exist because the left side limit and right side limit does not agree. That's why we say this partial derivative does not exist because this limit does not exist. This limit is how we define partial derivative. And the fact that this partial derivative does not even exist alone is enough to say this guy is what? Not differentiable. Okay, that is enough to say this guy is not differentiable. And that's the easy case. When the partial derivative does not exist, we say this guy cannot be differentiable. Thus, it's not differentiable. 0, 0. So obviously, the key issue here is, what if the partial derivative both exist? Is that enough to say this guy is differentiable? Okay, is that enough to say the function is differentiable? As we pointed out using this definition here, that's not always the case. Okay, that's not always the case. So when the partial derivative, we're talking about a function of two variables here. If they both exist, is f always differentiable at that point? So let me show you this next example. Does not work. So I guess this function itself looks simple enough. X to the 1/3, y to the 1/3. It's well defined for any x and y. But let's show for this guy partial derivative at 0, 0 exists. But f is not differentiable. Okay? So this guy looks innocent enough and looks kind of nice, but it's not differentiable. Partial derivatives, once again, is easy to calculate. So we just do fx here first. At 0, 0, right? So we're keeping the y value always at 0. And change x to h, and let h goes to 0. Well, if this is fxy, if this is f of xy, then actually both guys are both zeros because the y value is always what? 0. So this partial derivative at 0, 0 is actually always 0. All right. Same story for fy, okay? Same story for fy. So this partial derivative, they're both 0. So that linear arrow term, I want you to look that up. Linear arrow term is fx at this point times by delta x, and fy times the delta y. So the linear arrow is always 0. And when you try to calculate this difference here, so this is the actual arrow. This is the actual arrow. Of course, x naught, y naught, in this example here, they're both zeros. Okay, these are both zeros. So this is really delta x to the power of 1/3 and delta y to the 1/3. And back here is 0. So that's the arrow. The definition says the limit of this nonlinear part, okay, the limit of this nonlinear arrow over square root of delta x squared and plus delta y squared, where delta x, delta y approaches 0, 0, and this limit, okay, this limit has to be 0, okay, has to be 0 if you want f to be differentiable. For f to be differentiable. Am I right? That was how we define differentiability. But is this guy 0? Is this guy 0? This is not 0. One way you can show that this is not 0 is by doing the following. Okay, one way you can see this is not 0. It's not 0 because you can choose a specific path. You remember the different path we can choose when delta x, delta y goes to 0, 0. So one way I can do is I can always fix my delta y to be the same as delta x. So this is like along the path. And I'll simply set delta x goes to 0. But when delta y is the same as delta x, the top is delta x to the power of 2/3. The bottom is delta x squared and plus another delta x squared. This is clearly not 0, okay? It's power 1/3. This actually goes to infinity, okay? Just not 0, goes to infinity. The bottom is delta x. The top delta x are 2/3. So this goes to infinity. It's not 0. For this guy to be 0, okay, for this guy to be 0, this limit needs to be 0 along any path. This is just not true, okay? This is not true. You probably need more examples to see how this works. So let me work out one more example, okay? Let me work out one more example where a function is not differentiable. I take the absolute value and I raise this to the power of 1/2, okay? This is similar to the previous example. The previous example, the power was like 1/3. This is 1/2, okay, 1/2. Show that this is not differentiable at the origin. Once again, you need to be able to calculate the partial derivatives at the origin. And you can show this is 0. Now let's calculate the error at the origin. So I'm given a x value and y value a little bit change, delta x and delta y, minus the y value, the function's value is 0, 0. So this is really delta x times by delta y absolute value. So that's the actual error. And this will be equal to the linear error. Linear error in this example here, because those two guys are 0, this is actually what? This is actually a big 0. Linear error is always partial derivative times by delta x plus partial derivative times by delta y. But in this case, it's always 0. And so it's the nonlinear part is really this part here, okay? The high order term is really this part here. And this is supposed to be what? My epsilon 1 delta x plus epsilon 2 delta y. But the thing here is this part needs to go to 0. So once again, for f to be differentiable, by definition, this higher order term, this higher order error, over this needs to be 0 as delta x, delta y approaches 0, 0. So this needs to be 0. So is that 0? Is that 0? So once again, let's take a look. I'm going to try. So however, I'm going to try the limit along one specific path. Once again, I will choose delta x to be the same as, delta y to be the same as delta x. So I can just take delta x goes to 0. And delta y is the same as delta x. So you get delta x what? Squared. And down here, you have square root of 2 delta x, squared, which is clearly a constant. But the constant is not 0. This goes to 1 over square root of 2. Those two terms are the same. It's just not 0. So it is not differentiable. And in summary, if f is differentiable, then both partial derivatives have to exist. But the existence of partial derivatives alone does not guarantee differentiability. So existence of partial derivatives does not imply the function is differentiable.